So we were previously talking about a perpetuity. So if you kind of like disregard, you can disregard a lot of the mail here. And it really is a simple equation. I believe they haven't simplified it yet. You can either use this method, and here's some examples, but here's all you really got to know. This is the, and it's nothing more than first grade, uh, division here. The perpetuity is the cash flow, one cash flow divided by the interest rates, okay, that you're using. By depositing this amount today, we can withdraw interest of C each period forever, right? So if you put money in the bank and you take the money out, you live off it, right? You're living off the interest every year like some people do. That's kind of what they're driving at here, right? All right, so some people, and here's a good example, some people like endow money to colleges, and it's a perpetuity to pay student scholarships forever. So you're endowing a perpetuity. So let's show what that means.
Okay, so what you have here is a classic problem. The idea is donate enough money to your alma mater to throw a big graduation party every year. You figure they're going to need $30,000 a year forever. And so the idea is, what amount of money would you have to give them today, here at time 0, so that they would be able to have $30,000 a year forever? Even though what we're talking about is essentially the present value of an infinite stream of cash flows, there's two things to remember. One is it can have a finite value, and the other is that the formula is elegantly simple. So as we learn in the text, the formula for the present value of a perpetuity is just present value equals cash flow over R, where R is the interest rate that they'll be earning on the money that you donate to them. So in this case, we know the cash flow. The cash flow is $30,000 a year. We also know the R because in the column we stated that the interest rate is 8% on its investments. So we know that R is going to be 8%. So at this point, we just have to plug everything in. So we've got $30,000 is our cash flow, R is the 8%, and when you solve out for that, you get that the present value is $375,000. So that's the amount of money you would actually have to donate to them today, so that starting 1 year from now, they could start paying $30,000 a year for a graduation party. Now, how is it that you can start with a finite amount of money today and yet generate money forever for this party? Well, it comes from just thinking about what this formula is really telling you. If I just rearrange this formula, I have that R times the present value equals C. What is that saying to me? Well, it's saying that however much money I start with, that's the present value, as long as I really can earn 8% a year on it, then all I'm really asking the university to do is invest my money and earn the 8% on it. That's going to generate $30,000 a year from the 8% on $375,000, and just spend the interest. As long as they never touch the principal, the $375,000, they can continue to spend the interest forever, generating an extra $30,000 a year forever.
All right, so that was a good example, and let's move on here. All right, so now let's talk about annuities. And annuities is the same amount of money invested the same period of time. So it would be like a stream of the same amount of money, $1,000 a year for, let's say, every year, right? So that's what an annuity is, all right? At regular intervals. You see the word here? N equal, so here's the magic words. N equal cash flow at regular intervals. All right, so that's kind of like your mortgage. So here's how, whoops. So here's how we get the, what's going on here? Hold on. I don't know what's going on here. Here's how we get the present value of an annuity. I don't know what's happening here. It's acting up. So I think it's settled down now. How do we determine the present value of an annuity? And they show you the timeline, how it's done here, right? And basically here is the equation, the important equation 4.8. Okay. So basically this is the upfront cash in terms of C, right? So you can write this again this way. You could either write it that way, or another way to write it is this way. But again, we're going to be using Excel, so I wouldn't worry too much about that. All right, so what's an annuity do? So here's the magic word. The first annuity we did was an ordinary annuity. An ordinary annuity assumes the money comes in at the end of the period, and an annuity do assumes it comes in at the beginning of the period. Okay? So it happens at the beginning of the period. So all you do is use this equation here, and basically, it basically you present value it today. Everything comes back to today. Okay. So if you use Microsoft Excel where it says type, you put a 1 for an annuity due and put a 0 for ordinary annuity. All right. So let's go through this example here.
The lottery. Which finance professor has not been irritated by the claims of lottery makers? In this case, we have a lottery that's claimed to be valued at $30 million. The $30 million, of course, is just the sum of all the payments. But as good finance students will know that you can't just sum up payments in time. So what is a lottery that promises to pay $1 million for 30 years worth today? To answer this question, what we need to do is take the present value of the promised payments. So we begin, as we begin all problems, by writing the payments on a timeline. Notice that although there are 30 payments in all, the last payment occurs at the end of the 29th year. That is, the lottery payments are paid at the beginning of the year, so that the first payment is paid today and the last payment at the beginning of the 30th year or at the end of the 29th year. What this means is that we can think of the lottery payments as one payment today and 29 constant payments over the next 29 years at the end of each year. That is, we can think of the lottery payments as one payment today and a 29-year annuity. The value of the annuity today is given by the Annuity Formula. So let's go to the book and look up the formula for the present value of an annuity. Using this formula, we can calculate the present value of all the lottery payments by adding the value of the annuity to the first payment. As you can see, the true value of the lottery is only slightly more than 12 million, quite a lot less than the $30 million advertised by the lottery people.
All right, so that's that. All right, so now here's the equation for the future value of an annuity. And as I keep repeatedly saying, all this is in Excel. This is in Excel, and if I get a chance, I will make a video from Excel. So here's the present value of an annuity due. You notice they just add the 1 plus R to the end. Okay, so that's the present value of an annuity due. Okay, and there's some good examples here. So, go through these yourself. If you have questions, bug me. All right, so let's go through this example.
This is actually quite an important problem. Start saving $10,000 a year at age 35. How much money will you have at age 65? To answer the question, what we need to do is calculate the future value of the stream of payments. And to do that, we start by first drawing the timeline. Ellen is 35. So the first payment is going to come in when she's 36. And these payments will continue every year until she turns 65. So in terms of years from today, there will be a total of 30 payments starting next year and continuing for the next 30 years. Now, to calculate the value of these payments, what we need to do is calculate the future value 30 years from today. Now, the problem is I don't like to remember formulas. So my view is I should remember as few formulas as possible. So I don't really remember what the formula for the future value of an annuity. So instead, what I'm going to do is calculate the present value and then take the present value and compute the future value of that. Seemingly more complicated, but I think in the end it's a simpler way to go. Let's start by going to the book and finding the formula for the present value of annuity. Using this formula, we can take the $10,000 a year for the next 30 years and find the present value of those payments. Once we found that value, approximately $95,000, we can take that value and find what the future value is in 30 years, giving us $1.65 million. This very real problem might not seem relevant to you now, but in my experience, it becomes relevant sooner than you think.
All right, so I'm 12 minutes into this. I'm going to stop here, and I'll pick up on on part 4 here. All right, everybody.